Thank you. I'm Massimo Perini, and this talk is about deep learning, graphs, and streaming. So why deep learning and graphs? Well, because machine learning nowadays is everywhere, and graphs allow us to represent a lot of real-world situations where we have interconnection between data. So people in the last years tried to try to develop machine learning models that are able to also use the graph structure and the graph, the structure of the graph. One of the most popular models is Grapharis. Grapharis learns how to perform machine learning prediction, for example, vertex classification, given the vertex and the neighborhood vertices. So basically, it learns how to aggregate features from the vertices. This is an example of how Grapharis works. In this case, we are performing vertex classification. And as can be seen, Grapharis learns how to classify vertices into 3 classes. In details, how Grapharis works. In this case, we have a vertex D, and we want to predict, for example, a label of the vertex. We are sampling a neighborhood from this vertex, for example, 2 hop neighbors in this case. Vertex A and vertex B are 1 hop neighbors, and then we are sampling other neighbors from vertex A and other neighbors from vertex B. Since we have a 2 hop neighborhood, we are using two convolutional layers. First layer perform the aggregation between 1 hop neighborhood. In this case, D perform aggregation between D, A, and B, A and C and D, and B, F, and G. Okay, Grapharis works with assuming that on vertices we have features, a vector of features, and the first layer basically computes the aggregation between those features. So we can run, for example, a multi-layer perceptron over vertex A and vertex B, and then we can aggregate those the resulting vectors, for example, performing a max pooling or a min pooling, so taking the element-wise maximum or element-wise mean of the values of the vectors. And then, so we can, the first layer computes a vector out of every single subtree. And then the second layer performs exactly the same operation, but with other learned parameters. What are the problems that we are trying to solve? We try to solve 2 main problems. First one is that Grapharis requires a static graph. Grapharis learns how to compute embeddings given a static graph, and the available system perform inference, so perform prediction, only from static graphs. The idea is that we can then build something like this, where we have a label stream of vertices that we can use to improve our model, and then we can use the model to perform inference over an unlabeled stream of vertices. And in this case, we can generate embeddings or prediction or machine learning prediction of vertices. Okay, let's talk about the training part. How we usually train deep learning models. Deep learning model is usually trained with backpropagation. So we take some random samples from our dataset, we compute the output, then we compute the loss, so the error that our model has with respect to the expected output, and then we tune our deep learning parameters to reduce this error. What's the problem if we have a dynamic dataset instead of a static dataset? In a static dataset, taking random samples ensures that the model is equally trained over every single vertex in this case. While if our dataset is dynamic, we are biasing toward the old samples because we are always taking the sample with the same probability without taking care of maybe the fact that some vertices are older and some vertices are new. So the idea is that instead of taking poorly random samples, we can actually learn more from some samples or from some vertices in this case than from others. How can we measure, how can we learn from a vertex? A possible proxy is the error that our model has with respect to a certain vertex. So when we train our model, we compute the loss over every single vertex. That gives you a measure of how much the model is unable to predict the vertex. And we can use this value to actually bias the random sampling towards the vectors that are harder for the model. So basically that the model is not good is not having good predictions over them. While at the same time, new vertices can have maximum priority. In this case, when a new vertex is trained, we can measure the loss, and then we can detect if the new samples are, how our model is performing over new samples. Then if our model performs bad, we can keep training them more than others. This is an example of how the priorities are distributed over our dataset. As can be seen, darker colors means a higher priority over the vertex, and it tries to select more vertices that are near the decision boundaries of the graph. Now let's talk about the inference part. Basically, here we have a model and we want to generate predictions in real time. First thing is that, as can be seen, there are multiple duplicate computations if we simply take random samples and we run the convolutions over them. Because, for example, here in this case, vertex D and vertex G has many shared neighbors. So also the computation are shared, and we don't want to recompute them over and over and over. If you simply want to compute updates to our graph, we can use this method. So in this case, we are adding an edge between vertex A and vertex B. Here, since vertex A and vertex B have a new one-hop neighborhood, we are recomputing the one-hop vector. So the vector that B computes aggregating vertices from the one-hop neighborhood. And then, since the one-hop vector of A and B is new, we have to recompute also vectors of vertex D and vertex G. But, for example, vertex D doesn't need to recompute anything from vertex C because it is not affected by the new update. OK, this, of course, doesn't scale. What is the problem if we run an approach like the previous one over some scalable batch approaches for graph? The problem is that for them, they only work for batch and not for streams. So, for example, we can compute a new mutation or new inputs while a computation is already started. Or, for example, we cannot compute low latency processing. OK, the idea is that to use Flink, we can store in a keyed state where each key represents a vertex, some information about the vertex, like the vertex adjacency list, and the vertex vectors and the vertex neighbors vectors, as well as, of course, the neural network layers. The algorithm works in this way. For example, we have a new edge between vertex A and vertex E. So we transfer the information about the vectors of A and the information about the vectors of A that aggregates from vertex B and vertex C to node E. Node E then has a better understanding of the graph, and so we can re-infer over the vertex. How? We can compute the first layer, so the aggregation between E, D, and A, since A is a new vertex, basically. And this new vector is also shared with the neighbors of E. Then, of course, vertex E also recomputes the second layer and updates the prediction of the vertex. Vertex E, then, as I said, shares the new vector to the neighbors. In this case, for example, vertex D. Vertex D then knows that E aggregates also from A, and so it can recompute only the second layer of graph's edge and updates the prediction. And this this is the same as for all the other vertices, basically. How we implemented it? We can use Flink iterations to perform message passing between the different vertices of our stream. So in this case, for example, vertex E communicates with vertex A and vertex D, sending messages between them, and then the iteration rehashes them and delivers them to the right vertex. However, if we simply process every single update for every vertex, this process is not very light because we still have to perform matrix multiplications. So instead of processing every single message, we are actually processing windows of messages. And so we can compute the matrix multiplications only once instead of multiple times for every single incoming message. we used something like session windows to aggregate some incoming messages and to perform only once the new matrix multiplications. We executed the neural network, so basically the operation between matrices, with Breeze. Breeze is a library that performs efficient linear algebra, and it's been used also in Flink ML, SparkML, MLlib, and is efficient because it relies on the usually pre-installed Fortran libraries that are optimized for the hardware. So this is the overall execution plan. We have our stores of edges in this case, and in our Windows operator we are storing the graph. Basically, each key contains a vertex, and then the message passing relies on the iteration on the left, while on the right we are sending outside the new predictions of our graph. Okay, this works if our model is static. What if we want also to deploy new models while the system is running? We can simply, in this case, broadcast the new model to every single vertex. Then a vertex that receives the new model generates the new vector and sends the vector to the neighbors. Neighbors then, once they receive a vector from every single vertex, aggregate them, and then so perform the aggregation and resend to the neighbors the new aggregated vector. In this case, for example, he received vectors from the neighbors and then is sending to the neighbors again the aggregated vector. So this is the overall execution plan if you want also to use dynamic models. In this case, we are broadcasting the new model, while the other operations are more or less the same. We still have a problem, that is the fact that Flink may have deadlocks while it runs iterations. We fixed this using a prioritized input. So we are giving higher priority to the iteration input over the standard input, because the iteration will be finished sooner or later, while the other input not. Okay, so we ran some experiments both for the part of training and for the part of inference. We are using two different datasets. The first one is Pubmed, is a publication network where every vertex is a paper, and there is a link between papers if there is a citation between two papers, and we want to perform inference over the topic. So, for example, machine learning papers or distributed system papers. In Reddit, instead, we have a vertex for every post, and we have an edge if the same user comments on both posts. And we want to infer the community of the vertex. For the training section, we have three baselines. The first one is the offline training, so the standard way of training neural networks, but also more expensive. The no rehearsal trains only over the new samples, while the random trains only over taking random samples from the graph. As can be seen, okay, the first one is the Pubmed plot. The higher the curve, the better is the result. And as can be seen, the main difference is here at step 16, when we are adding a new class in our input. And our method is better than the others, because it achieves sooner better performance, because it's giving higher priority to the new samples that are, in this case, harder, because our model is not able to predict the new class. And we can also see that at step 80, we have a drop for the no rehearsal, because in the input stream, we are only having a single class, so our model is overfitting over the class, over the single class that we have in our input. So basically, it's forgetting how to classify the other two classes. Same for Reddit. Reddit is a more evenly distributed dataset, and in this case, however, our model is still better than the random one, at least at the beginning. This is the training time. Of course, our model is static because we are running a fixed number of backpropagations, while the offline method runs multiple times backpropagation and then for the entire dataset. This is the scalability throughput, the scalability of the online inference method compared to a single thread performance. As can be seen, our method scales with the numbers of workers. We used 1, 2, and 4 workers, each one with 4 task slot. And we tried also with different window size. As can be seen, the bigger the window size, the higher the throughput. But at the same time, the bigger the window size, the higher the delay. For example, this is Pubmed, and at the left we have the delay that takes for a message to reach the first vertex affected, while at the right we have the delay, the overall delay. So basically, the time that is required to spread the update over the entire neighborhood. And this is the same for Reddit. However, we are still under 1 second, more or less. That's it.
Maybe I missed this point, but how are you connecting TensorFlow into this whole graph here?
TensorFlow outputs a series of matrices, basically matrices, and then we are importing the matrices using some library that reads NumPy files and then loads the matrices into Flink.
Okay, so you're sending the training data as messages to TensorFlow and then taking the output as well?
Yeah.
Yeah.
Okay, yeah. Thank you.
Thank you.